So that last problem set is going to be chapters 14 and 12. The problems are there on the board. They're also in the OneNote and on My Notre Dame and in the grade book. Reminder again that 2 homework assignments are being dropped. So if you've completed all the homeworks up until this point, there's, you don't need to like lose any sleep trying to complete this one on time or anything, or even completing it at all. Obviously, you should do the work enough to like know what you're doing, because chapters 12 and 14 will be represented in that final, but just putting that out there. Also, if you have not yet emailed me to let me know whether you wanted to do a doubled high test score or to do a chapter test or chapter retake, let me know kind of as soon as you know. I think all the test grades, if you've taken it, the tests are in, maybe with 1 or 2 small exceptions. But as soon as you know what you want to do, shoot me an email and I'll start entering whatever those are. If you're electing to do a retake, we'll try to do it one of those days next week. We'll probably do that on an individual basis once I figure out who's doing what. And then I also put into the content library, this is the equation sheet that's going to come with the final. So again, as you're making your notes, probably good to have that so you know, like, hey, I'm wasting my time putting this in there because it's already on the equation sheet or whatever. And then I put a blank version of the chapter tests that we've done so far, as well as a old version of 14, and I guess I called this 13, but it's supposed to be 12. You guys will let me slide on that, I hope. Oh, you know what? This is flat out the wrong thing that I meant to put in there. So I'll fix that here today. Let me delete that.
That'll work next time.
Yeah. I just flat out did the wrong, put the wrong chapter in there. So I'll fix that here in a little bit. To put in 12 rather than 13. I just plumb put in the wrong chapter. All right. Any questions about any of that stuff here before we close this thing out? All right. Today we are going to finish chapter 12. Well, start and finish chapter 12. What we're going to be doing here in chapter 12 is going to be all done in the calculator. So if you have your calculator with you, I'd encourage you to kind of pull that out so you can follow along with stuff. And if you don't, and you want to run and grab it from your locker, you're welcome to do that real quick. Otherwise, you're just, do the best you can and watch what we're doing. You know what I mean? If you want to look on with a friend that does have their calculator, that's okay too.
Do you have a charger up there?
I do.
Yeah, can I come?
Yeah, of course, man. Sure thing.
Thank you.
Yeah, my pleasure. All right. So what I want to do, or what we're going to be doing in chapter 12, is basically going to be creating regression equations. So ostensibly what we're going to be doing is we're going to have some data, And our calculator is going to turn that into some type of equation. So the different types that we have, or that we're going to deal with, would be linear, quadratic, cubic, exponential, logarithmic, and then power. So all of these types of equations, other than power, are something that we've talked about this year. Oh, I forget what the... Let's see. I forget how the calculator formats that. Let me try that real quick so I can put that in the right way. There we go. Okay. Okay. So those are the 6 different types of regression equations or models that we can make. Okay. So one way of deciding which one is to make a scatter plot, which is basically just means plot the data and look at the picture. So if it looks like a line, you know, you'd want a linear equation. Right? What's a quadratic going to look like? A parabola. What's a cubic going to look like? You know, something like that. What's an exponential look like? You know, like a hyperbola is the name of that kind of graph. You know, logarithmic looks kind of like that. And a power can kind of look like anything. So notice in the power equation, the independent variable is the base, and the exponent is the part that we'd be finding out. So that, like, a power function could look like a quadratic or a cubic, or, you know, something else like a squiggly, you know, it's pretty versatile. So that gives you a good intuition, at least initially, of like which one of these might be the best match by looking at the graph, right? But, you know, like sometimes even it's like, both of these, you know, like this thing that might be exponential could just be like half of a quadratic. You know, which one is really the better piece, right? You can see that. So there's another way of looking at that. And so that's going to bring us to the the topic of correlation. So correlation describes how linear some data is. So the symbol we use to describe correlation is the lowercase letter r. And correlation exists on a continuum. So correlation is always bounded between -1 and +1. 0 means there's no correlation at all, that the data is like perfectly random. That's kind of a theoretical value. In the real world, you wouldn't really get data that's perfectly random. 1 means that this is perfectly linear with a positive slope. So that means that all the points in your data, you can create a line that actually passes through all the points in your data. And -1, again, is also perfectly linear, but this time with a negative slope. And the closer you get to 1 or -1, the better fit that linear data is, or that a line would be for that data. Let's say as the absolute value of r approaches 1, that means either r is going to -1 or +1, right? Okay, so let's go and so what about nonlinear data? Right, what do we talk about there? We use what's called an r² value. And this is called the coefficient of determination. And it's similar to r. As r² goes to 1, the better the fit. Okay, so let's do some examples now on how to use our calculator to do some of these problems. Sound good? Okay, so let's say we have this data set. So I'm going to go to enter data into my calculator. I'm going to press the stat button. From the edit tab, I'm going to select the edit command. So there you should see your lists, L1, L2, L3, etc. Now my lists have something in them. Yours are probably blank, but if they do have something in them, you can delete entries individually by pressing the delete key on the entry, or you can wipe an entire list by moving your arrow or moving your cursor up onto the list name, pressing the clear button and then the down arrow, and that'll wipe everything in the entire list. So if you have a bunch of stuff in there, that's helpful. Don't press delete when your cursor's on the L1. It's a pain in the butt to make it come back. It's not impossible. Mr. Kulik can help you if you do that, but try not to do that. Okay? All right, so I'm going to type the independent variable into L1 and the dependent variable into L2. You can tell from the heading of the data here which one is the independent dependent variable, right? Should be pretty clear there. So I'm just going to type the number and press enter, and the calculator will automatically toggle my cursor to the next spot. Oops. Okay. And if you make a mistake, you can always go back and like type over top of the old number, or you can delete it out, type a new number in. If you skip one, it's kind of a pain in the bunzos, because I don't know that there's a good way to like add in one number. I'm not sure if the insert option will work in the table or not, so do your best not to skip something without realizing it right away, because you might have to just like retype everything from where you skipped the one. So I pressed the stat button, and then from the edit tab I selected the edit command. Sure. Okay, so then my data is into my calculator. So the first thing I'd probably want to do is probably look at the scatter plot to figure out like, okay, what does this data look like? To graph a scatter plot on my calculator, I press second and the y equals button. These are the different scatter plots. You can plot up to 3 on your calculator at one time. I'm going to plot using plot 1. I'm going to begin by turning it on. The first option that it defaults to is the scatter plot option. I type my x coordinates into the list L1, and I type my y coordinates into the list L2, so that's already by default there. If you typed them into a different spot, you'd have to type in a different list name there. If that was the case, notice above the numbers 1, 2, 3, 4, 5, 6 in blue is L1, L2, L3, L4, L5, L6. So if I did L3 and L4 instead, I could type L3 and L4. Now I didn't do that, but some of us might have. It looks like, oh my goodness, what did I just do? Looks like Blake was just about ready to ask that specific question, because as soon as I started saying that, he put his hand down.
Yep.
Okay. And then the last option just tells us what the points on our graph are going to look like. I like using the boxes because they're easier to see, but that part doesn't really matter. Now, to get my graph to show up reasonably, what I like to do is use the zoom option. Oops. Come on now. So I'm going to use zoom, And then the option I'm going to want to pick is zoom stat. So here the calculator is going to automatically pick a window that fits the data in your data table. Oh, Boise, what is that thing? That looks like Mr. Kulik typed a number in wrong. Yep, look at what he did. Let me go fix that real quick. All right. Okay. So, what shape does this kind of look like to you?
A line.
Okay. I mean, this part of it looks like a line, but this tail, well, I would say it's exponential, except it's starting to level off here at the top. My bet is that a cubic is going to be our best fit. The other option would be a logistic. We're not going to worry about a logistic, though, right? Remember, logistics kind of look like this also. That's probably what the best fit for this would end up being, but I didn't list that as one of the ones we're going to worry about, so we're not going to worry about it. Now notice that like 3 of us had 3 different ideas of what to do here, right? So how would we be able to tell which one of the 3 of us was actually right? You know, like Sydney had an idea, Blake had an idea, Mr. Kulik had an idea. What we could do is we'd ask the calculator to generate the regression equation for each of these 3 and look to see which one had a better coefficient of determination. So which one had the better R² value. So let's start by looking at Blake's example. So what we're going to do now is generate some regression equations. So to generate any regression equation, we start by pressing the Stat button. And we're going to move over to the Calc tab. And options 4 to the end, I think, are all the different regression equations. So lin reg is a linear, quad reg is quadratic, there's cubic reg, quartic is a degree 4 polynomial. There's another lin reg one. I don't know why they feel like they need to have the option where the A coefficient is on the X and one where the B coefficient is on the X. It seems really silly to me, but like, whatever. Here is the logarithmic. So they call it ln reg because they're using a natural log in the equation. Exponential reg, power regression. There's a logistic regression option, a sinusoidal regression, and then there's like a manual fit option. We won't use those last ones there. All right, let's say we did the lin reg one though. So let's pick that option. So it's going to default me into this menu. It's going to ask me what is my X and Y list. So I used L1 and L2. The frequency list will always be blank when we're doing the regression equation, so that can just be left blank. I am going to store the regression equation in case I want to do something with it later. So where you'd want to store this is into one of the Y spots, Y1, Y2, Y3, so that you could look at the graph of it later, use it to evaluate something. So I'm going to go ahead and I'm going to put this first one into Y1. So I'm going to do vars, yvars, function, and I'm going to pick Y1, and then hit calculate. When you did this, how many of us were missing the R² or R values when you did this? Okay, let's get those to show up then. So if you were missing the R² or the R values, or you don't have your calculator here to follow along with, you'll likely have to do this. So the easiest way to get those to show up is we're going to press second and then the number 0. This opens up the catalog. This is an alphabetized list of every function on your calculator. The function that we're looking for to make those R and R² values show up is called diagnostics on. So we're going to scroll down to either that, or if you notice there's a little green letter above a bunch of the buttons, if you press the button where the little green D is above, it'll scroll all the way down to the D's for me already, which saves me a lot of button pushing. I'm going to scroll down until I found diagnostic on. Did we find that? I'll press enter to select it back to the main screen and press enter again to where it says done. Now, if I press second and enter twice, that'll bring back up my previous regression. And if I press enter to execute it, your R and R squared value should show up now. Did that work for you guys? Okay, so that's a pretty decent R squared value. Not bad, right? You're over 0.9 is pretty close to 1. Not an unreasonable estimate. The other choice you guys thought was exponential. So let's do the same thing. Let's see what the R squared is for the exponential. So what is that? 9289. Okay. So to get the exponential reg, we'll go back to the stat menu, over to the calc tab, scroll down till we find exponential reg. I'm going to store that regression equation into y2 this time. And then hit calculate. There, the R squared value is slightly worse, but pretty close still. Oh, I did quad. No, I did exponent. Okay. And that was 0.9205. Okay. And then Mr. Kulik was suggesting that maybe the cubic looked like a good fit for that. So let's do one more. I'm going to store that into y3. Oops. And look at the R squared on that bad mama jamma.
Hey.
It's almost like Mr. Kulik knows what he's doing here. Yeah.
Can you go over getting R squared again? Because I'm very confused.
Okay. Press second and the number 0. Then press the button where the little green D is above it. That'll scroll you down to the D's in the alphabet.
Okay.
Scroll down till you find diagnostic on.
Got it.
Press enter to select it. Press enter till it says done. Does it say done?
Yes.
Okay. Then now they'll show up next time you do a regression.
Thank you.
You're welcome.
So you don't want like you don't want a number that approaches 0, correct?
Correct. The closer you get to 1 or -1, the better the fit is.
Okay.
Everybody's cool with that? Okay. So once I have a model that's pretty good, I can use that model to make predictions, right? So for example, if I wanted to know like what W of 58 is, I can make a prediction on that. So which one of these models would I use to make that prediction? The one with the best R squared value, so the cubic. Remember, I stored that into y3. So I could do y3 of 58. And that looks to be about 3404. Just for grins, let's see what we would get for our prediction if we did the same thing for our exponential and our linears. Just to see, because we got them, right? So let's see, the linear or the exponential I put into y2. Oh, it's a lot different. And the linear, I think we put into y1, right? That was the first one we did. So 2771, 34, 22. I don't know, I just picked 58. So like this would be like what would W of 58 be, you know, or something here. I think that was a 71 though. Yeah. So you can see, even though exponential there wasn't a lot of fit difference, the prediction was quite different between the exponential and the cubic, for example, or the exponential and the linear. It had very similar values. Just to illustrate kind of what's going on, what I'm going to do is I'm going to look at the graph here. So I'm going to make the exponential with a thick line and the linear with a thin line, and we're going to look at it compared to our scatter plot. So there's our linear. There's our exponential. So our exponential does pretty good in the beginning, and then kind of right here. And then after that, it's going to be kind of bad there and kind of bad in here. The linear is kind of bad in the beginning, pretty good through the middle. And then just for grins, we'll turn these off and turn the cubic on, and you can see visually what's going on here. So there's our cubic, which looks that's pretty tight. Everybody okay with that? Now, there are two types of predictions that we can do. The first type is interpolation. That's what we did here when we took W of 58. So that's where you're making a prediction about a value that's in between the independent variables that from your data set. So notice 58 is in between the biggest and smallest of the independent variables in our data set. That's interpolation. Katie? Sure. Now, interpolation tends to be pretty accurate. Because what is your model being based on? The numbers in your data set. If this is something that's plausibly in between the numbers in your data set, it's unlikely that there'd be some kooky behavior going on inside the middle of the data set that you don't have a measure of. The other type of prediction is called extrapolation. And that's where you're making a prediction outside the independent variables in your data set. So extrapolation can be very unreliable. So for example, if we wanted to look at maybe W of 1,000, so let's do that same thing here with each of our three models. So that y1 was the linear model. y2 was our exponential model. Wozers. And then y3, I get there. Probably would have just been easier to look that back up. Any of these look really reliable? Oh, heck, I don't know. Right? They're massively different. Extrapolation. And then to be even more of a stickler, these were actual measurements from something, right? I'm guessing this is like the length of something and the weight of something. So like, if it's an organism, is it likely that that organism is going to weigh 3.18 times 10 to the 40th, whatever we're measuring that weight in? Unlikely. That's a massive, massive organism. And it certainly couldn't be negative. So we're having like some pretty kooky looking potential measurement or predictions because we're using this extrapolation. Maddie. Sure. So extrapolation can lead to a bad prediction. What else could be, what else can cause a bad prediction? What's another reason that a prediction we make might be bad? Jillian. Okay, so like what you mean is really like bad data, right? So your data is in some way unreliable or something. Okay. Sure. What else could happen?
If you don't have enough data points, is that considered bad data?
We can say that. Kind of falls in with another topic or another one that I had in mind. How about just you pick the wrong model, right? Like you pick something that didn't fit the data very well, and you're using that wrong model to make predictions. Would that be probably not reliable there? Let me give you another example. Let's say we wanted to create a model to predict the the height of individuals based on their age. Okay? And all of our data set were taken on people that were like ages 3 to 10. You think that's going to work out very well? Why not? When are you growing the most? During that kind of time, right? So you're going to end up with something that says, oh, at age 40, you're going to be like 75 feet tall, which is bonkers, right? So I would call that like biased data. So you're over-representing some group. This would be kind of the same as too few data points. You don't have enough to cover like all behaviors, rather than taking people from like all possible ages, randomly selected. Or if you did the same thing and say, oh yeah, we're going to take people of all ages, but these are all, like future, former, or current like professional basketball players. Again, like height is going to be super overrepresented there. Or if all of your people are men. Again, men on average are much, like 6 inches taller than women. It's going to be a poor model for picking out women. So like bias in your data is you're just not taking a very good sample. Everybody feel okay with that idea? Okay. In what you're doing, what is going to be the major source of error? Would be these two, right? Somebody asks you to extrapolate in the problem. Is that a reliable? No. Or they ask you to like use a blah, blah, blah model and then make this prediction. The model has a crummy R² value. Not going to be a good prediction. Everybody feel okay with that idea? One more thing I think I wanted to say. What was it? I can't think of it now. Maddie.
I have a question about like the final with like chapter 12 and chapter 14.
Sure. What's up?
Is it gonna be like the same thing, like you're gonna take problems from that one test?
Mm-hmm.
Or like variations of those?
Mm-hmm.
Okay.
Yep, exactly right. Yep. Oh, this was what I was gonna say. Okay. Is extrapolation always gonna be unreliable? No, it might not be, right? And in fact, when is extrapolation gonna be potentially the most reliable?
Do you have a good R² value?
Well, not even necessarily that. More so, what I would say is if it's actually close to the ends of your data set, right? Like if I wanted to make a prediction about when the length is 74, that extrapolation might not be too bad of a prediction. You know what I mean? Because it's fairly close to the data. But if I wanted to find, when length was 1,000, you saw the craziness that we got with each of the 3 different models. They were all over the place. You know what I mean? So that's the key with extrapolation. If you're extrapolating rather close to the end of your data set, you tend to get a pretty decent still prediction. But if you extrapolate way far out from the end of your data set, who knows what you're going to get. Can you think of a real life example of where that prediction comes in? It's probably something you look at every single day. The weather. What weather prediction is relatively accurate? The weather for tomorrow. If I look at the end of the 10-day forecast, is that going to be as good as the weather for tomorrow's prediction? Tends not to be. Or if I try to look at like the Farmer's Almanac and predict like a year out, probably not great. You know what I mean? So that's another example of something like every day where it's like, oh yeah, we're extrapolating here. But if we're at the end, like relatively short in the future, we're pretty good at that. You ask them what the weather's going to be like in a month, you can be way wrong on that one. You know what I mean? Now you can make a decent guess based on historical trends or whatever and be like, okay, like in the middle of June, the average temperatures for the past 30 years have been something like this. And you can like work that out. Maybe you're, the odds are you'll be okay, but you just might catch the coldest day on record or the hottest day on record and be way off. You never know. Extrapolation's hard like that. Yeah. Well, really, yeah, for sure. Okay. Do we feel okay with this idea? Again, for the most part, the calculator is doing all of the work for us, right? We're using the calculator to get the R squared, or the R and the R squared values. We're using the calculator to create the models. We're using the calculator to make the prediction. All we're tasked with, the hard part for us is Did I pick a good model? Am I making a good prediction? You know, like, can I operate my calculator to get it to do what I want it to do? You know, it's like most of this is just going to be kind of interpreting what you're getting. Okay? That's it then, guys. We're going to be El Dunzos.